All right, so let's get started. So sorry for the delay, some technical difficulties today. Are the lights correct? Yes, it was just extremely bright outside. Okay, where? Pixel. All right, great. So today we're talking about hypothesis testing. We're starting hypothesis testing. Probably if you think about statistics, if you've heard about this before, it's probably maybe one of the first things that comes to mind of what are statistics good for. They're good for hypothesis testing, things like calculating a p-value, perhaps. These are maybe things you've heard of. Yeah, so who thinks they can define a p-value? All right, it's fine. Yeah, it's kind of tricky. We will see this and you'll understand it by the end of this sequence of lectures. We probably won't get to p-values today, but so next week, right? So these are the sort of things you do with hypothesis testing, and we've been kind of building up to these all semester. It's not the only thing you can do with statistics and probability. We've seen other useful things to do, right? But hypothesis testing is kind of, I mean, these was important in that it kind of kicked off the entire scientific paradigm in some sense. So kind of hypothesis testing was crucial in the development of that. There are other starts of that around the same time, but this was a key piece of that, which is still kind of it's still an important part to understand these things. So we will talk about this, but I will introduce it through this tea tasting experiment, which was, if you believe some historical accounts, kind of the first case of this hypothesis testing framework. And it's one where there's kind of, you can see exactly what's going on there. Where in a lot of cases, hypothesis testing is used with kind of not carefully. They kind of they'll kind of press a button and out comes a p-value, and they'll say, yay, or, oh man, I need to go back and do it again, without really understanding what that means, right? So in the tea tasting experiment, you'll be able to kind of understand this kind of from somewhat of a first principles point of view, and then we'll look at the more general version of these things. As we like to do, let's look at the schedule. Where are we? We have 3 lectures on hypothesis testing. Looks like we will do, some stuff in R. We'll see how to do this in R as well. When I got to this section, I realized I didn't have complete notes to lecture from. So I'm kind of where I've had them from before that I've kind of been updating as I go. But not having to change too much for this section, I realized I didn't have them. So I'm kind of writing them a bit now. So I haven't updated the link under this, the middle column yet, but I'll do that. It's got today's lecture in it, but it's incomplete on the next few lectures. And then I wanted to add in something different I haven't covered before, permutation testing, which will kind of be a very powerful and general tool, which is very computational. So in that sense, it's a very new tool. Hypothesis testing is over 100 years old, well before we could do stuff with computers. Permutation testing is something that's we can do this because we have computers that can do a bunch of stuff for us. Right, and then we'll start to wrap stuff up. So, okay. Homework 6 is out, copies up here. Starting to get a few questions about it, so you're working on it. Hopefully, mostly pretty straightforward. So, okay, great. All right, hypothesis testing. Where are we here? Okay, so I'm going to start with a with the story, I guess. So this was a story from so Ronald Fisher, who's one of kind of, I think, the founders of statistics, and he was telling a story, so he's also in England, like William Gossett. So if you remember William Gossett, who kind of derived the tea distribution of the first version of it, was working at Guinness Brewery. This is also from the British Isles. He was in England, and so he was not drinking beer, but was having a party. And what do they drink in England if they're not having beer? More of a upscale party. Maybe they're having tea. Yes, yeah. Oh yeah, I broadcast that in the first slide. Great. Okay, so tea. They're having tea. Okay, and the story goes, there was a lady at the party. This lady was talking about how if you have tea plus milk, and if you put them in the cup, do you want to put the tea in first or the milk in first, right? There two options. Tea first, or milk first. All right, and this lady at the party claimed that she could there was a difference, and that she could tell the difference between whether you put the tea in first or the milk first. All right, so Ronald Fisher was like a mathematician. He's like, I think I can design an experiment to test whether you can actually tell the difference, right? So his idea was to have 8 cups. So these cups were going to be prepared in the kitchen. The lady was not going to be in the kitchen, and he promised that 4 cups had the tea first, okay, and so 4 cups had the milk first. All right, and then he was going to present all of these 8 cups to her. She was going to have to test them all, and decide which ones had the tea first and which ones had the milk first. All right. So this was the experiment. All right, and so we're going to kind of walk through the probability associated with this experiment and look at the results and see if the lady, for instance, is able to guess all 8 cups correctly. How convincing is it that she actually could, tell if the tea was first or if the milk was first, right? Kind of, there were 2 views on this, and I don't know exactly the story, but there were 2 views. The first view, we're a bunch of computer scientists in here, so we'll start with like the 0th view, and we'll see why this is in the next lecture. We'll see why I start with 0, I guess. But so that in like the 0th view, we'll say that the tea first or the milk first has like the same effect, right? So basically, it's going to be like a random guess. Okay, so for each T, she's basically, if the lady is basically going to have to guess at random. Okay, and so like the other view is that so she can so tell the difference. Yeah, okay. So now, if the lady is guessing at random, though, she might get them all correct, right? But if she can tell the difference, it could be, well, maybe she can usually tell the difference. It could be if she has 100 cups, she might not get all of them correct, right? She might get, say, 99 or 98 correct out of 100 cups. But in this experiment, we have only 8 cups, right? We could reanalyze this with more cups, but she might not get them all right, but she should be able to do so better than random, right? Can she do so better than random? Can she convince Fisher that she could tell more than random whether the tea was first or the milk was first? So, okay. So this first view, this guess that everything was random, this is going to be known as the null hypothesis. All right, so this is kind of the basic hypothesis. If you don't think you can tell the difference, I was in the departmental kitchen today, and someone was making some coffee and was pouring some creamer while the coffee was coming out. I'm like, oh, so can you taste the difference if you put the creamer at the same time? And he's like, no, I can't taste the difference. So I'm just in a hurry. I'm like, so that's the null hypothesis, that you probably can't taste the difference if they're put in first or if you mix it in together, right? So that's our baseline. It's some simple model. We think, okay, this is a boring explanation of what's going on. All right, and then we're gonna see if we can, possibly, like, can we maybe try and all we're going to be able to maybe say is, can we reject this null hypothesis? Okay, that we think she can do, that some people can taste better than just random guessing. All right, it's not clear we'll be able to determine like at what rate she could guess correctly, if she could guess correctly, but we'd like to see, can she do better than random? Okay, so let's try and write down the probability here, let's write down the actual events, right? So we're going to think of a table here of like the possible outcomes. So we're going to have like the columns will determine the lady's guess, and it's either going to be milk first or tea first, right? And so then there's going to be the truth, right? The person in the kitchen is going to know which cups are which, or the tea first. All right, and then we can look at the possible outcomes. All right, and so we're told that in this case, the lady is told they're going to be 4 of each. Okay, so she could guess something like, well, I'm of them that her guesses could look like this, but it's going to have to look something like this. In this case, 3 of the ones that said, she was going to guess 4 things had the milk first and 4 things had the tea first, right? And So in this case, she got 3 of the guesses for milk first right, and 1 of the guesses for the milk first wrong. And so with knowledge that's 50-50, this has to be so like symmetric like this. So either it can be 3-1-1, it could be so it could also be it can be 2-2-2-2. Okay, so that this would be kind of the modal outcome if you expect it's going to be random. If she was really good, then maybe you would think, okay, she could get all, so like it's like all 8 of the cups right. But it could also be possible that you know, that she's actually not very good at this, and if she's guessing at random, you know, it could be 1-1-3-3, or you could have something like this, where you have 0-0. She gets 0 correct, so in everything wrong, right? So these are all possible outcomes, right? And so we're going to, instead of drawing the contingency table, so we're going to say that we're just going to choose the number of the milk first, so that she got correct, right? So this will be K. So K is 3 for the blue one. The purple one, this is K equals 2. For the green one, this is K equals 4. This is K equals 1. And so K equals 0, right? These are the, if she knows they're going to be exactly 4, and she matches, she's very confident, so she's going to match her guess and say, I'm only going to get so 4 of these, 4 tea first, 4 milk first, then these are the only outcomes. So okay, so let's look at this. So this like green case of, so all correct, right? So this green case where she guesses all 4 of the milk first correct, meaning that she actually got everything correct. Let's look at the probability that this actually occurs. Okay, so the probability of getting everything correct in this case, so it's going to be there. So there only one way of getting the right selection out of the number of ways to guess, right? So there's only, so if she got all of them correct, then there's only one way to do that. But if the which was tea first, which was milk first was random, then we need to say that probably they're all correct is 1 divided by the number of possible ways to guess this, right? And so what's the number of possible ways? Well, there are 8 cups, and exactly 4 of them are going to have some milk first, right? So how many different ways, how many different combinations can you have 8 cups with 4 of them have the milk first, and 4 of them not have the milk first? Remember this from Yep, that's right. Yeah, so the answer is, what we'd write as 8 choose 4. There are 8 objects, and we're gonna, if we have like an urn with 8 cups in it, we're gonna choose 4 of those 8 cups out of the urn. How many different ways can we choose? 4 cups, right? So this gives the number of guesses if the lady is guessing at random, right? So it turns out that this is 1 divided by 70, right? So 8 choose 4 is going to be 70. And so this value is approximately 0.014. Okay, great. So what is this saying? This is saying that if she was indeed guessing at, so random here, right? If she was indeed guessing at random, the probability she would have gotten all 4 correct is about so like 1.4%, right? 1.4% of the time, or the probability 0.014, probability of getting everything to guess correct, right? So yeah, so this seems like, so if she could get all correct, this would actually be pretty convincing, right? There's less than a 2% probability that she would get everything correct if she was guessing, right? So if she can get them all correct, then you could say, well, I'm willing to reject the null hypothesis that you're guessing at random. It would have been a very unlikely, less than 2% of the time, less than 1.5% of the time, would you have gotten everything correct if you were just guessing. Yeah, okay. Right? So this was a design of an experiment. And so, so I think the story goes that Fisher, did some back of the envelope, the calculations and said, if we bring out 4 cups, or these 8 cups, half with tea first, half with milk first, and you guess, and if you get them all correct, then I'll believe you, right? That would have been, you may have gotten lucky, but it happened a small enough, probability time that you'd get lucky that I would actually believe you. Right, so this was kind of, this was the basis of the first hypothesis test. All right, so this makes sense as an experiment. Something to try and do, right? This is fairly specific, right? She had, it's exactly 8 cups. There's a promise that 4 of them were milk, 4 of them were tea, and that in order to convince Fisher, she was going to have to guess everything correctly, right? You might accidentally make a mistake or something, or so Fisher could have played a trick on her and said, well, only 5 had milk first and 3 had, so tea first. So that would have been trickier, but that's not included in here. All right, so yeah, so let's first, before I talk about hypothesis testing more in general, let's just generalize this experiment, just to see this a bit more. We're in general going to be looking at a truth table or a contingency table where you have k, 4 minus k, so 4 minus k and k, where this is, the first thing was milk or tea, and milk or tea first, and this was the lady's guess, and this was the truth. Okay, and so and there's something, so the probability that governs this is called a is a hypergeometric distribution. Okay, and this is defined, to define a distribution, I need to define the probability for every value of k, right? So I can define that as the probability for k, and this is for k equals 0, 1, 2, 3, up to 4. That's the number of guesses correctly. In this case, that's going to be 4 choose k, 4 times 4 choose So 4 minus k divided by 8, choose, so 4. Okay, so where does this distribution come from? What we already saw was that the denominator was 8 choose 4. That's the number of ways that that the cups could be arranged based on tea first or milk first. And then so then the ways you could get 4 things correct was or the number of ways you can get so k things correct was 4 choose k, and then given that you had the milk correct, you had 4 minus k things of the tea that were incorrect, and you needed to choose which one of those was incorrect. Right, so these are the total number. The numerator, the top of the fraction, is the total number of outcomes where you could guess k things correct. All right, and so turns out you can simplify this to 1 over 70, which is the denominator. 4 choose k, so squared, right? 4 choose 4 minus k is the same thing as 4 choose k. And so what we're actually interested though is would this still have been so convincing if she had only gotten 3 of the milk cups correctly, right? So 3 of the milk cups correctly, and also 3 of the teacups correctly. So she had to guess 8 cups, and the next best she could have done, other than all 8 correct, was to have 6 correct. Would this still have been convincing? All right. Yeah, right. So it'd be less convincing, right? So the probability of getting like 3 cups correct, that should be you should have more chance to do that random, right? So let's figure out what that is, and then we can decide if that's convincing, right? So I see there's a question in chat. Yeah. So the table is, the row is always the guess of the lady, and the column is always the guess of the lady, and the row is always the truth. Yeah. So, okay. Right. So if she had guessed 3 things correctly, that seems like that's more likely to happen at random, right? 4 choose 3. So let's see. 4 choose 3 is going to be 4, right? And so 4 squared is going to be 16. So that's going to be 16 out of 70, right? But what we actually want to, so if we evaluate this in a table, right? So this is the P of K, and this is the value of K, or let's do this the other way around. We'll say K is at the top and P of K is at the bottom, right? So you can get 0, 1, 2, 3, or 4. Okay, and the probability of 0 correct is going to be just as hard as getting so what we calculated before was probably getting 4 correct was 1 divided by 70, right? The probability getting 0 correct, to get 0 correct, you have to get everything exactly wrong, right? So you probably have to know the difference, just mix up which one was which. But the probability is going to be the same, okay? The probability of getting 3 correctly, right? 4 choose 3 is going to be 4, and 4 squared is going to be 16, right? So this is going to be 16 out of 70, and so by symmetry, the probability of getting one correct is also going to be 16 out of 70 if you did this at random. Okay, and then these need to add up to, so 1, right? So the last number should be, so 36 out of, so 70, right? Let's check that. 36 plus 16 times 2, 32. That should be 68 plus 2 is, so 70. 36 is also 4, choose 2 is going to be 6, right? So 6 squared is, so it's going to be 36, right? So okay, so how should we look at and consider the case of if she got 3 things correct? So 16 out, so 70. Well, that's not exactly what we want to look at, right? What we'd like to look at is the probability that she got at least 3 correct. So if we thought 3 was a good threshold, so so let's say we're doing this with 80 cups instead of 8 cups. It'd be impressive if she got 39 out of 40 instead of, if she got 40, it'd be great, right? But if she got 39 out of 40, it would also be good. So typically what we want to say is the probability that that you get 2K correct or better, right? So you want to look at so if you have a distribution here, you want to say something is interesting if you're getting that correct or better, so it would be unusual. So why is this the right thing to do? So let's say, I want to say I could, yes, okay, so let's say, so you're doing something where you're, so you think you can, control a die, and, but it's not like a fair die. And the probability of getting, what's the right way of, explain this. So let's say that there's this, probability distribution. If instead of this one, well, let's say I had a different, probability distribution. I was, the goal is to get a, high score. Okay, and I think I know how, I know how to get a high score. And so the probability of getting a score, if I'm playing at random, right? So I have S of K, which is the score. This is the value. Right. So K is the score, and this is, let's say this is the probability of getting the score K. Okay, and so it could be that it's 0, 1, 2, 3, 4, 5, 6. And so if I look at this table, it's actually easier. Let's say probability getting a 6 is like 1 out of 10. If I were to play the game at random, maybe this was 1 out of 20. Let's say this was 2 out of 10. 3 was, 2 out of 10 was 2 was 2 out of 10. This was 1 out of 5. 1 out of 1 was 1 out of 20. 0 was 1 out of 20. 5 was 1 out of 20. All right, my goal was to get a high score. Okay, and I said, well, what's the probability I could get, 5, right? If I look at the probability of 5 of K equals to 5, this is equals to 1 out of 20, right? So this is a low probability, but if I wanted to get a score which is higher, right? This probability if I played at random was going to be like 1 out of 10, right? So which one's more impressive? That I got a score of 5 or that I got a score of 6? Yeah. Well, if my goal was to try and get a high score, to say I'm good at this game, I think I can get I can score very high in this game. It's not going to be I'm good. I'm a better player than random. Okay, so I want to argue I'm a better player than random. What's more impressive, getting a score of a 5 or a score of a 6? Score of a 6 can't lose, right? A score of 5, you might lose if someone else random plays, and 1 out of 10 times they're going to beat you because they're going to get a 6. So the score of the 6 should be more impressive, right? So how do we take this into account if the score of 5 has a lower probability of happening? Yeah, so I'm saying, let's say I know that if I use the AI, right, in the game, it's going to get a score with, this probability. I'm playing or think of there's a dealer rule of like blackjack or something. There's some sort of random process, and that random process will give me these scores with these probabilities. And I think I'm better than that random process, right? I want to demonstrate I'm better, right? So now, which is more impressive, a score of 6, which is the top score, or a score of 5, which is not the top score, but is a lower probability? It should be the score of 6. But my goal is the highest score, right? So 6 is better. So I set this up so it was a little, it's like not intuitive, right? Because we started by saying we just could look at the probability of the event, and if the probability of the event is really small, then this should be impressive, right? But that's not quite the case here. 6 should be more impressive. It's a better score, right? So let's say, I'm playing like skee ball or something, and I think I can get like 6 balls into, like the highest scoring thing, right? I'm trying to throw, I'm trying to make a bunch of free throws. What's more impressive? I can get 6 free throws or 5 free throws. And there's an AI that says, I think I'm better than the AI. The AI is a robot, and if it's calibrated correctly, it will get all 6. If the calibration's a little off, it might get 5, but if it's more random, it'll do something else, right? It's not this is a distribution I made up. Yeah. Yeah, so is it impressive if she could guess them all wrong, right? Maybe, but not if she was trying to guess them all correct, right? So yeah, so I'm trying to argue that k equals 5, that outcome is not as impressive as k equals 6. And the right way to think about this is look instead at the probability that k is greater or equal than 5, right? So instead compute the probability that you don't get exactly 5, but that the outcome, that x is greater or equal than k, instead of x equals k. Okay, this was x equal k, this is x greater or equal than k. Okay, now if I extend this probability table or this outcome table, this is 1, right? The probability I get greater or equal than 0 is 1. The probability I get greater or equal to, 1 is going to be 19 out of 20. Probably I get greater or equal than 2 is going to be 2/10, 3/10. What, so like 7 out of 10, right? The probability to get greater or equal than 3 is going to be, so 5 out of 10, 50-50, right? Greater or equal than 4 is going to be, so 3 out of 10. Greater or equal than 5 is going to be 3 out of, is that 3 out of 20? Or did I mess something up here? What? Oh, I didn't get them to all add up correctly. Okay, so if I change this to, so symmetric, maybe that works. Yeah, okay. So this would be, so we happen to be making an example. You get 1, 2, 5, 7, 8. No, I need something more, right? 6 out of 10, 7. I need some. Let's make this one, so 2 out of 10. Here, let's make the first one, so 2 out of 10 here. Okay. All right, so now let's fix these scores. Okay, so this should be, this is 8, no, plus 1 out of 20. So I'm going to have 15 out of 20. Right, that I did a score of 1 or better. Right, and then I'm going to have 11 out of 20 that I get 2 or better. I'm going to have 7 out of 20 I get 3 or better. Going to have 3 out of 20 that I get 4 or better. I'm going to have yeah, and then no, I should have, I'm off a little bit here again. Of 1 should be, oh, but I get that or better. So that should be 16 out of 20. It should be, oh, strictly greater. Yeah, if I do, I should be doing greater or equal than is the thing I want. Okay, so then I should just add up everything before. Okay, this time I'm going to get it correct. I'm pretty sure. So this one should be 16 out of 20. Yeah, great. Then this one should be 15 out of 20. This one should be 11 out of 20. This one should be 7 out of 20, 3 out of 20, and so 1 out of 10. Right? So, okay, so this tells me how impressive it is if I get the probability that that so gives me that value or larger. Okay, so I only get to just count the last term if I have just this value. So I only get 1 out of 10. So if scoring 5 should not be as impressive out of scoring 6, I have a kind of the probability I got that score or better, so is 3 out of 20, which is not as impressive as getting 6 out of 20. If I have an objective, then I want to try and maximize. I want to reach a certain value or possibly do better. Okay, this is also important if I'm doing this with a continuous distribution instead. Right? Because the probability of getting exactly some particular event, that probability is not defined, or you say it's 0. right? So you want to say that probably you did exactly that event, or you did better than that, right? So okay, so let's go back to our actual example here, and now we can write down kind of how impressive a certain thing is. Okay, so the probability of getting 4 or better cups of tea is 1 out of 70 still. The probability of getting 3 or better, right? So the probability that the number, so uppercase K, is greater or equal to K, this is now not 16 over 70, but is 17 over 70. Okay. The probability of getting 2 or better, this is not too, should not be too impressive. This should be 53 out of, so 70. This should be then 69 out of 70, and getting 0 or better is going to be 1. So right. So this is telling me how impressive it is. I want to say I want to be able to get that value or better. Okay. So 17 out. So 70. What's the probability of that? So you want to have a calculator? Yeah. What's the probability if she had guessed 3 correctly? Yeah. So about 0.24, right? So okay. So if she was guessing at random, then about a quarter of the time, about 24% of the time, she would have gotten 3 or 4 correctly, right? So 3 or better correctly, right? So would you have been convinced if she had guessed 3 of the cups correctly? Yeah, so not really, right? So maybe that could have happened, right? That's not too unlikely, right? So, so this number doesn't seem too impressive, right? If that could have happened a quarter of the time, well, yeah, that could have happened. I'm not totally convinced. But if she guessed all 4 correctly, then that happens about, right? So remember this one. So the probability of K greater or equal to 4, this was approximately, so 0.014. So that happens less than 2% of the time. That's pretty convincing, right? So this was, the basic premise. Yeah. Yeah, so we're looking at the outcome and we're saying, how likely would you have scored that well or better, right? We're gonna after this, we're gonna move to continuous distributions, right? So we're gonna say, how well would you have scored that good or better? Oh, if your goal was to guess 2, so then you would have set the experiment up so differently. Just guessing at random, slightly more than half the time, right? If you look at 36 out of 70, this is slightly more than half. 35 out of 70 is half, right? So if my goal is to do that, I can just guess randomly, and half the time I actually get exactly 2 correct, right? Or you're getting half correct and half incorrect, right? So even just doing that under this experiment would be, is not too impressive. Now let's say she had 80 cups of tea, right, and wanted to guess exactly 40 of them correctly and 40 of them incorrectly, right? So like, how far are you from being so from getting exactly half. And you can measure the cumulative distance, right? We're doing so we're doing kind of, like the backwards version of the CDF, right? So you can measure the cumulative from the distance from the target value. You could set up some experiment like that, right? So if you set the t-spacing experiment is just kind of the first one. It's one where you can calculate the probabilities exactly, right? And we can look through and you can think through if you'd be convinced. And then we're next going to look at like we have like you're assuming like a normal distribution, right? It's a little bit harder to actually work through the actual probabilities, and you have to kind of conceptually get what does 0.014 mean, right? 2% of the time. It's a little bit easier to see it here. Yeah.
So we did trial of this same experiment done over and over again. If the lady was able to guess 3 times pretty consistently, that 0.24 result would start multiplying against itself. We'd be much more confident about.
Yeah, right. So if we reran this experiment and she got 4 cups or K equals 4, right? So 8 cups correctly twice. That's I believe that'll be the same as running the experiment with just 16 cups total. But maybe there's a party, she has enough tea, she's like, no more, had enough tea, I'm a little bit kind of hyped up, and then come back the next week and they do it over again and she does the same thing. Yeah, so then those would be independent trials. What would the probability of getting all 16 cups be? Can you get that easily from this?
It would be 1 out of
70. Yes, it's been 1 divided by 70 squared, right? With independent kind of events you're measuring, then they're independent, so you can take the joint probability is the product of the individual probabilities, right? So I take 1 over 70 squared. Now I'm going to be kind of 0.00 probably 0 something again, right? So a pretty small probability. She'd done it twice, 2 parties in a row, then you'd be like super convinced. Yeah. So great. So okay. So good. So let me kind of how is the bottom row calculated again? I calculated this question on Zoom. I calculated basically the probability that she's guessing the 2. I mean, let's just look at the milk cups, right? And say that she's guessing K or more milk cups correctly, right? Of the milk first cups, right? So it's a cumulative density, but summed up from the right-hand side instead of from the left-hand side. Yeah. So okay, so let me summarize kind of some points about general hypothesis testing, and then we'll kind of go through this with kind of some normal distributions and think about this from a more generic point of view. So next time, okay. So summary of, so I'm going to kind of preview the general, procedure for doing a test. Okay, so I'm going to go through these steps a bit more. So next time, but the first thing we want to do is to define the null hypothesis. Right, so we want to define the null hypothesis. Okay, so we want to say, what is the baseline that we think is actually going to happen? All right, so part of this is actually designing the experiment, right? So I'm kind of setting up the I'm gonna observe, I'm going to observe data, and here's what I kind of, the baseline, here's the simple explanation of what's gonna happen, right? So then, so assuming that the null, so hypothesis is true, then you want to say, so determine the probabilities of the outcomes, right? So once I have a null hypothesis, the null hypothesis might be something more general, like I think she's guessing at random, but then I actually want to say, well, if she's guessing at random, then I need to map this to this hypergeometric distribution, right? And with the hypergeometric distribution, I can say there are only these 5 possible outcomes in my experiment design, and I can determine the probability of all those possible outcomes, right? Right. So now I can determine the possible outcomes, and then I can collect the data, and then compute the probability that the data was more so that that the data's outcome, let's say the probability of the data outcome, or something more extreme. All right, so we want to say, because this could be a continuous space of outcomes, we want to say the probability that you did as well as you observed, or possibly something even more extreme than what, right? Yeah. What does more extreme mean? Right, so this depends a little bit on the experiment, but you kind of want to score all of the outcomes, right? You want to say, everything we're going to think about in this class is going to have real value outcomes, okay? And so you're going to say that value or larger. We're going to think of, we want to get a largest possible value. We want to say that value or larger. There will be some cases when we want to say that value or smaller. Smaller is more extreme, and we're willing to accept something smaller, or we want to say it could be in either direction, on either tail. But in this class, this semester, we'll just say in the upper tail. We want to get the larger possible score. Well, the null hypothesis is a probability distribution, and when you actually collect data, right, you no longer have a probability distribution. You have a particular value. Well, there's not a, so let's go back here again, right? So I set up the probability table. I haven't told you what the outcome of this experiment was yet. Okay, this was partially by design, and then I was going to tell you, and then I forgot to tell you. So it turned out in this case that the lady by the story actually got all 4 correct, right? So so Fisher was convinced, everyone was happy, right? He invented hypothesis testing, right, as well. But if she had guessed 3 correct, that would have been a particular value, or like 6 cups correct, right? So 3 of the milk cups correct. If she had gotten 3 of the milk cups correct, right? That's one value here. There's no longer a probability distribution, right? So the null hypothesis has a probability distribution. The actual outcome is a constant value, right? So there's not like, okay, well, I could say, what's the mode of the distribution? The mode is the most likely outcome. That's a 2. Okay, well, it wasn't the mode, right? I could say, what's the expected value of the outcome? The expected value is 2, right? Well, it's larger than the expected value. It's fine, but like how much larger? How much is in the tail, right? How unlikely was that event or something more extreme to have happened? Is a larger value. That's usually the case. Sometimes you want a smaller value, right? So you want to say, I have a new, so treatment for COVID, and I think it works well. So you want a small number of people to get sick or to die as possible, right? There you want that number or smaller versus the baseline distribution is the population rate of infection or something. And that might be some other value. And you want to say, well, my rate of infection is smaller, right? So then you want to say that the experiment you would reject the null hypothesis that it worked the same as doing, the baseline if the number of infections was, 2 or smaller, right? And you saw 2 infections, right? So you say the probability of 0, 1, or 2 infections, the sum of those, then you'd reject on the small side, right? Yeah, you can do bidirectional things. So I will reject it if it's too far from the middle. You can set these up in a variety of ways, but you can define what it means to be more extreme. We're mostly going to say it's larger. Okay, so we'll just kind of say if it's larger than what I expect. Yeah. All right. Okay, another super important thing about here is that there's this line here before and after we collect data. You need to do kind of 2 things before you collect data. You need to make your assumption on the null hypothesis. Okay, and then you need to calculate, and all the probabilities and the probability distribution is set at that point. Once you've done that, this is before you collect the data. If you've already collected data and then someone tells you, now look at the data and tell me if it's, if it's going to be significant, you should say, no, don't show me the data, but tell me what you want to do and then design a null hypothesis and then go and look at the data. Okay, you shouldn't look at the data and then decide, oh, this looks kind of like a normal distribution, so I'll use that to define my distribution. You should decide by nature, right, or what you think the prevalent kind of way of thinking is above the blue line before you go and collect data. Okay, so this is the fundamentals of like statistical, hypothesis testing, where you don't look at the data until after you've formed your hypothesis and you've worked out all the probabilities. I mean, you can work out the probabilities later because they're a derivative of the hypothesis, but they exist before you collect the data, assuming you made the hypothesis first. When doing data science, like machine learning and stuff, you often look at the data during the process of the analysis of it, and you need to kind of not just blindly use this, sort of framework. In the world of science, in like biology and stuff, a lot of these labs will run really expensive experiments. It might take them a year or 2 to actually collect all the data and stuff. They will pre-register their hypothesis online someplace. And people have developed a system where you can register it, and it's like, the hypothesis is like encrypted, and you can reveal, give out, you don't want to tell other people what you're working on, so they might try and steal your idea, right? So you put it up there and you encrypt it, and then after, when you collect the data, then you go and reveal what your hypothesis was, to convince people you did it in the right order. Because if you make a hypothesis, your null hypothesis, after you look at your data, you can come up with a null hypothesis that makes the data look good. There are tricks you can play, and maybe we'll talk about those a bit later. But so it's important to keep these sort of things separate. And to back in the picture of like machine learning has developed an alternative framework to this. You still use statistics in various ways to analyze things, but a different framework than this that's still valid, where they can look at the data and help form a hypothesis from the data, but not kind of cheat the system in some. Okay. Okay, but that's gonna be like a story for another day. Okay, I want to stop now because you have a quiz. Not actually stop the lecture, but do a review for the quiz. Okay, which is going to open in 10 minutes. This week was split between finishing up confidence intervals and starting the hypothesis testing. Okay. I'm not going to tell you exactly what part will be on the quiz, but I'm going to review important information. Yes. Okay. So let's go back and think about what we talked about for the confidence intervals, right? For the confidence intervals, we start with a sample x1 up through xn, and these are IID from some distribution, and then we're going to create a statistic, right, which is going to be a function of x1 up through xn, and this is still going to be a random variable, right? So this is still going to be a random variable. Well, what we'd like to do though is to trying to understand this parameter, right? And so in most cases, most of what we talked about is that this distribution was a normal distribution, okay, with a mean and like a sigma squared. We talked about if this was a binomial distribution as well, which in the limit kind of approximates a certain type of normal distribution. But with the normal distribution, we talked about two cases. Okay, so either and then if we're dealing with this, we often want to estimate mu, and we'd like to say get some bounds on the true value of mu, and then the 1 minus alpha, and kind of, I know for some this is confusing how this is written, times 100%. So confidence, interval, okay? And for example, e.g. if alpha equals 0.05, then this is a 95%, right? So that's a typical thing we would look at. So that put alpha, 1 minus alpha times 100 times percent. That's how that works. So the confidence interval would then be two values L, N, and so in Rn, it defines this interval, and these are going to be some random variables. And we want this so that the probability that ln is less than mu and Rn is greater than mu is exactly 1 minus alpha. 1 minus alpha. Okay, so that's the confidence interval. Okay, and how do we get ln? So ln is going to be xn bar, right? Remember, we often do xn bar. This is 1 over n. I equals 1 to n of xi, and it's xn bar minus. So there's going to have two parameters here. There's going to be some value we look up at a table, and then something divided by square root n. Okay, and so there are going to be two options here. One option is that this is going to be z alpha over 2, and this is just going to be sigma squared, or not squared, it's just sigma, if we know, so if we know sigma squared, then the z alpha over 2 is going to be equal to the probability that x is, or so is the alpha over 2, is the alpha over 2, so 1 minus alpha over 2 quantile of the normal distribution. Okay, but then the thing we talked about on Tuesday was when this is xn bar of t alpha over 2, and this is the sample square root of the sample variance, so the sample standard deviation, divided by square root n. And this is if we do not know, so sigma squared. Okay, so then we use what's called, then t alpha over 2 is equal 1 minus alpha over 2 quantile of the t distribution. Okay, and so the t distribution was like the normal distribution, but it's slightly wider so than before. Okay, and the Rn is if you add these instead, right? Yeah. So the Sn, let's review that. Remember, Sn squared is the sample, so variance is going to be xi minus xn bar squared. This is the sample, so variance. Okay, so square root of Sn squared is just Sn is going to be the sample standard, so deviation. And that's also, these are both so random variables, right? So because Sn is a random variable, then this expression is more complicated. We need to factor in that there's randomness in that part too, and that's why we need to change from the normal distribution to the t distribution. And the t distribution is the distribution which factors this in appropriately. Let me just say the t so distribution, okay, is defined. You can have a random variable from t, and it's n minus 1. It's parameterized by what's called the degrees of so freedom. Okay, and because you used up one of the, if you have n samples, you use up one of the degrees of freedom estimating so the sample mean or the sample standard deviation. So you only have you have n minus 1 of these things, and so this so it's parameterized by this, right? So you have to sample, so that should have fit down here in the bottom right, but I didn't have room. Okay, so the t distribution is similar to what you do here to do this confidence intervals for the t distribution is similar to what we did for the normal distribution, but is when we do if we don't know the variance, then we have to switch to this. Okay. Okay, what does it say after z alpha over 2 plus or minus alpha over 2? At the, yeah, so it says, yeah, so this said z alpha over 2 is the 1 minus alpha, so quantile of the normal distribution, and t alpha over 2 equals the 1 minus alpha quantile of the t distribution. This might be written as, yeah, and you might write this as, making my font too small again, but of like t of n minus 1, right? Instead of, in place of the normal distribution, you can use t of n minus 1 is so the parameter. Yeah, so this is what, so this is instead, you can instead write the same thing, the t alpha, down here, the t alpha over 2 is equal to 1 minus alpha over 2 quantile of the t distribution. So I just rewrote that here. Yeah. Yeah, so this was, and then today in the lecture, we set up hypothesis testing. And so, yeah, but so hopefully this was a review of what you'll need for the quiz. And so next week we will kind of finish up hypothesis testing, and then we'll kind of start wrapping up this semester. Question? Okay, can you say that again? Oh, okay, yeah. So in the normal distribution up here, right, there are two parameters, sigma and mu. Let me just write out, if we have f is a PDF sigma squared from the normal distribution sigma squared, then we can define, this is a PDF, so that means we can define it for a value, it's a function of a value x, and this is defined as e to the negative x minus mu squared divided by 2 sigma squared, divided by 1 over square root 2 pi times, so sigma, and you can kind of visualize this as mu, and there's some distribution that looks fairly so symmetric. This would be the PDF of f mu sigma squared, and roughly halfway up, the distance to this is roughly, so sigma, this is what the standard deviation is. Okay, so mu turns out to be the expected value, the mean, right? So the expected value of x, if x is drawn from a normal distribution with mu sigma squared, then the expected value of x is going to be exactly mu. Okay, so it's the expected value of that distribution as well. And sigma and the variance, yeah, and variance of x equals sigma squared. So right, so okay, Great. I will end the lecture here.